Please take your seats. Our program is about to begin. Please welcome Peng Wu from Meta.
Yeah, I'm waiting for the music to go down. Good morning, everyone. Please take a seat. And also, we have an overflow room to that side if you cannot find a seat. I'm very excited to open the 2024 Triton Conference with two exciting tutorials. We'll have the first speaker, Keren Zhou from OpenAI and George Mason University. He will talk about how to write Triton kernels using tools, specifically the Triton interpreter, if you want to debug an illegal memory access problem, and the profiler, Proton. And this tutorial will be 1 hour and 10 minutes. The second tutorial is from Haishan Zhou from Meta. He will talk about the backend of Triton, which is the MLIR compiler, and he will demonstrate how to write a compiler pass doing a vectorized addition. And this tutorial will be 45 minutes. And we do not have Q&A during the session, but we do have a speaker's office hour, which I've never heard before, but I love the innovation here, which will be 4 o'clock this afternoon at the same time as a happy hour. With that, let's introduce Keren.
Oh, cool. Hi, good morning. Nice meeting you guys. It's my great pleasure to kick off the Triton conference this year. And it's very glad to see so many of you are interested in Triton and came to the conference. So in this talk, we are going to cover a few topics about tools for Triton. So in the past few years, I've been leading developing third-party tools that support developers to write better Triton kernels and debug its performance and correctness. So in this tutorial, we do not have strong assumption that you are very familiar with Triton. We just assume that you have heard of Triton before and you're familiar with Python and PyTorch. That's probably the reason why you come to this conference. We do not assume you are a GPU expert, and we don't assume you're a compiler expert. The learning outcomes of this tutorial is that you should be able to understand the challenges of debugging and profiling Triton programs, learn how to use Triton interpreter for debugging Triton programs, and gain some familiarity with using Proton, our profiler, for performance analysis. Here's the outline for today's tutorial. So since this is the first talk in this Triton conference today, I'm going to kick off with some review of Triton basic syntax and Triton's design overview. Next, I'm going to dive into core components of Triton, including interpreter, Proton, and an experimental feature in Proton, which is instruction sampling. All right, let's start with reviewing Triton. Triton could be a lot of things. As you know, it's a Python-like language, and it also has a JIT compiler. It's also a PyTorch backend nowadays. It also consists of a set of MLIR dialects. It's also an organization and a community. Here are the major components of Triton. So there are a few entry modules of Triton, which are things that we maintain in GitHub, like in Triton's repository itself. So on the front end, we have Triton language, and on the backend, we have official support for AMD and NVIDIA GPUs. Between it, we have profiler and interpreter that connects Triton frontend with Triton backend to help you better write your Triton programs. There also exist third-party out-of-modules on GitHub, including support for Intel GPUs, CPUs, and also accelerators. So Triton is a Python language designed for high flexibility and performance in deep learning application. It supports tensor interface similar to PyTorch, which means that you can use tensor operations similar to whatever you have when you use PyTorch. The difference is just that these tensor operations operate on Triton tensors instead of PyTorch tensors. All the syntax we use to write Triton programs are quite similar to Python. There are just very few exceptions. But compared to CUDA and Rackham, Triton simplifies GPU programming by only requiring knowledge that the kernel is divided into multiple blocks. In our terminology, it's Triton programs, and most underlying details for optimization have been handled by Triton compiler itself. Here's a brief overview of a simple Triton kernel. Usually I use 1D FacAdd, but I think it's probably to add more stuff to make it 2D FacAdd. So in this kernel, we're going to add two tensors, x and y, and accumulate the result into another tensor, z. Each tensor is a 2D tensor with dimension dim0 by dim1. So let's look at this code snippet. To declare a Triton kernel, we're going to use a kernel decorator, triton.jit. Then the kernel definition is just as if you are writing a simple Python program where you supply parameters like the pointer to tensors and its dimension. One exception is constant expression, which I think that could be constant during the kernel execution. Okay, then let's jump into function body, which has a set of Triton operations invoked. At the beginning, we're going to get the program ID, which specifies where your current program instance, which is analogous to CUDA block, is located. So since we have two-dimension Triton tensors, we need to get to the two-dimensional indices, which are referred to PID x and PID y correspondingly. Then to locate which offsets we need to operate in each Triton program, we need to compute its offset using PIDs. Then we create Triton tensors to create offsets from 0 to block time 0 and 0 to block time 1. After that, we still need to check if our offsets are out of boundary using masks, which is a Boolean tensor that specifies which locations are within the boundary and which locations are outside the boundary. In the end, we are going to invoke memory operations, tl.load and tl.store, to load tensors values from GPU's global memory to Triton device memory or registers and perform an add. After that, the output is going to be stored into GPU global memory, again using tl.store. So hope this reminds you how to write in Triton kernel if you haven't done it for a while. But in the next, we are going to dive into the core parts of the tutorial, including interpreter and the profiler. We're going to begin with the interpreter, which is like a debugger. To begin with, I want to diverge from the main topic a little bit and demonstrate cases where debugging GPU execution could be difficult. Let's start with a simple CUDA program. This is 1D factor add. So basically, we are going to allocate GPU memory with element size of 384 for both array A, B, and C. Then on the device, we're going to invoke a GPU kernel factadd to add up A and B and store the results back to C. So this seems to be a simple kernel. However, it's possible that some beginners of CUDA or GPU programming, like new beginners in my class, may make some silly mistakes. They could invoke a GPU kernel with 4 blocks, where each block has 128 threads each, then obviously when the last block is going to access the 385th elements on the GPU global memory, it's going to throw an arrow. The arrow would be something like runtime error, CUDA error, an illegal memory access was encountered. And it is noteworthy that this kind of problem seems to be easy to observe and resolve, but in production workloads, it's going to be difficult to debug even for experienced engineers. So our colleague, Greg, there was once a time, he went to sleep at 3:30 a.m. and trying to track down a nasty CUDA illegal memory access bug. He woke up early to keep digging and finally push a fix. Sorry, Greg, but back to that time, we don't have fully functional interpreter yet. But thankfully, he's on vacation now. Hope when he's back, he's going to enjoy new functionalities in interpreter. In addition to out-of-bound memory access problems, there are also other problems existing in GPU programming, including the following. For example, global memory data race, which happens when multiple threads are trying to access the same location. In this case, the results you get finally might be incorrect, consisting of some values you don't expect. There could also be improper synchronization when you have producer and consumer pairs that tries to produce values and consumed by other blocks. In this case, it's going to cause deadlocks. There's also memory leaks where tensors are not freed after use. It's not common in PyTorch, though, because GPU memory is handled automatically by PyTorch's memory allocator. Besides, there's also misaligned memory access, which can report errors similar to out-of-boundary memory access. It happens when you are trying to use factorized memory instructions, but the tensor allocated is not aligned. So although Triton has been trying to simplify GPU programming a lot, debugging Triton programs is still not easy. You still could have out-of-boundary memory access problems and other problems we have seen before, because we are still need to launch parallel program instances. For example, in this case, we have specified parallel instances in 3-dimension x and y, z. And to access GPU memory in each Triton program, we still need to calculate offsets using pointer arithmetics. And when trying to access multiple dimensional arrays, trying to avoid some out-of-boundary memory access, we need to supply additional fields like mask and others. That's why we designed the Triton interpreter, which can be think of a debugger that allows users to debug Triton programs as if they were debugging standard Python program on the CPU, which because of Python, it doesn't allow multi-threading. It's just going to execute each Triton program serialized. So using Triton interpreter, it allows you to attach PDB to step through each statement interactively, and allows you to print tensor values as multi-dimensional arrays for better visualization. As I mentioned, it serializes the execution of multiple Triton programs for easier debugging. Okay, so before introducing the use of Triton interpreter, I want to remind you some background context about Triton's front end. So we begin with some Triton programs written in Python. Then to generate executable binaries, the Triton compiler is going to invoke a module called code generator, which is going to iterate over the AST of the Python function. In each in each Triton operation, we're going to go through a few semantic checks and match it with the core Triton operation. Then each core Triton operation will be lowered to a Triton IR by a IR builder. This Triton IR is already in MLIR dialect. Then going through a few backend transformation, the Triton IR will be lowered to LVM IR or other assembly code. Then finally, we'll invoke assemblers from different hardware vendors and compile it to binary executables. So using the interpreter, we're going to replace the code generator. We don't visit the AST and generate IRs anymore. Instead, we just iterate and traverse your Python program as if we are just executing each Triton statement. We still maintain the semantic checking and mapping to core Triton IRs, Triton ops. This is the most convenient part of Triton interpreter. You still go through semantic checks and maintain the same semantic as the native Triton. Then in the backend, we replace the IR generation part with the interpreter builder that maps core Triton operations to NumPy executors, which generates equivalent statements as the Triton program. So here's an example of executing a Triton kernel using interpreter. At the first, we're just going to prepare CPU tensors because there's no GPU support for the NumPy. So suppose your PyTorch tensors are originally stored on the GPU, then we're going to prepare CPU tensors by copying their values from the GPU to the CPU. Next, we're going to invoke the interpreter to convert each Triton ops to their equivalent NumPy operations. Then, meanwhile, we are going to serialize your program execution. Each Triton program previously running in parallel are now serialized so that we're going to run them one by one. We are going to start with program 0, following program 1, and then end up with program 8. Suppose we have 9 programs. After the execution is done, now we have got the results on the CPU. If the tensors were originally stored on the GPU, we need to copy them back and update their values. So this ends up the introduction about how the interpreter works. After that, I want to give you a few demos to illustrate how to use interpreter. It's actually kind of simple and just include very few knobs. First, suppose we want to debug something like out-of-boundary memory access using native Triton debugging statements like tl.devicePrint or tl.deviceAssert. This is what we are going to do. Using our original 2D tensor add example, we are going to insert a new statement, tl.devicePrint, between line 9 and line 11. We are going to print the offsets values for each Triton program to see what their exact values are and see which program has out-of-memory offsets calculated. And on the right side, this is what we are going to get on the terminal. We will have thousands of statements printed out because we have a lot of programs, in this case 8x8 programs, and each program is going to print a lot of statements because it also has a lot of threads. So on this right side terminal, we are going to see on each line, it specifies the program ID, which in this case 65. This is PIDX equals to 6 and PIDY equals to 5. And IDX specifies which location of the original tensor the value comes from, and following with offsets value. This is probably not very convenient, at least for me, to debugging the out-of-bound memory access problems. Instead, when we switch to Triton interpreter, the only thing we have to do is to export an invariant variable Triton interpret equals 1. Then instead, we are going to replace tl.devicePrint with the normal and standard Python print statements with print offset equals the offset value. Then here's what we get. We can get a tensor value for each program, which is a 8x8 tensor, I assume in this case. So that you can view the offset values as if you are printing values on CPU, like printing out the NumPy or PyTorch tensors. In addition to print statements, we can also attach PDB in the interpreter mode. Suppose we are just interested in specific programs, like PID 00, we can insert if statement, and within the if statement, we can import PDB and invoke PDB.setTrace. This is going to work in the interpreter mode. What makes it more convenient is that it seamlessly integrates with development environment like IDEs such as Jupyter Notebook. We can just set up a breakpoint on the left. Then using the Jupyter Notebooks view, we can easily view each variable's name, its type, and its values. The same thing is going to work in other developer IDEs as well. But the interpreter cannot solve everything. It does have limitations, I have to admit. The first limitation is about precisions. Some floating types, like float 8 and float 16, support only a limited number of arithmetic operations in interpreter mode. However, this is also a limitation on the hardware itself. Suppose you want to add up two float 8 values together, it's not going to be supported on GPUs anyway. You need to cast it to float 16 for addition because there's no such instructions available natively on GPUs. Also, currently, interpreter doesn't support debugging concurrency bugs. For example, if you have pairs of consumers and producers, and you suspect that there are some problems because they didn't communicate properly, it's not something we can debug because we always invoke programs in the order from 0 to n. There's also another problem we don't support yet, which is indirect memory access. Support the original PyTorch tensor stores, instead of values, pointers to the other tensor. Then in this case, we load a pointer PTR1 from the original pointer PTR0, and then we're going to access the value stored in PTR1. We don't support this case yet. Okay, so this ends up the introduction to the interpreter. In the next, we are going to talk about the profiler, Proton. Proton just stands for a profiler for Triton. It's designed to provide a quick, intuitive, and simple way to check kernel performance. It's fully open source. It's included in the third-party directory in Triton's main repo. It currently already supports multiple vendor GPUs, include AMD and NVIDIA GPUs. It can offer flexible metrics collection, including hardware metrics and also software metrics. The main functionality it's offered currently is call path profiling. So to give you some more context about how Triton's runtime works, let's diverge it to this diagram to show you how that works. So let's see, we have both activities on CPU and GPU, where the CPU is responsible for compile and launch kernels, while the GPU is responsible for executing the kernels. For each individual Triton kernel, we're going to calculate a hash using the input tensor values, constants, scalars, and its source code. Then we're going to inspect and check if the hash is already being manipulated and handled by the Triton runtime, and see if we have a cache miss or cache hit. So here, cache miss means that the cache miss means that DRAM doesn't have the corresponding kernel object yet, and the disk probably also doesn't have that kernel object yet. In this case, we need to compile from scratch. We need to compile the Python source code and lower it into IR, and then finally generate new kernel object. Then we're going to update our cache table, and after that, the sim hash will not be missed again. Otherwise, if we got a cache hit, that means we have already compiled this kernel. Then in this case, the only thing we need to do is grab the corresponding kernel object. After the kernel object is in DRAM, we are going to launch it, given the tensor, constants, scalar. Then the launched kernel will be offloaded to the GPU. Here's how Proton, the profiler's runtime, works. On the CPU, we're just going to launch kernels as usual, or we launch kernels without intercepting it. And each kernel will be offloaded to the GPU. On the GPU side, we use vendor-provided libraries like Cupty and Racktracer. It's going to profile each kernel asynchronously with CPU kernel launch. And each kernel metric is going to be accumulated on GPU buffer. Only once the GPU buffer is full, we're going to copy them back to the CPU, and Proton is responsible for accumulate these metrics onto the call path where these kernels were being launched. Currently, we support different aggregation methods, including sum and average. We don't support mini and max yet. Here's a design overview of Proton. It supports two interfaces, including the command line interface and the instrumentation-based interface. The command line interface is relatively simple. We just prepend Proton as a prefix before your Python script. And instrumentation interface does require modifying your source code to apply some annotations. Then the core library consists of both kernel metrics handling and also invoking the corresponding vendor-provided measurement substrates, including CUPTI and rack tracer. After the profiling is done, we're going to output the profile into hatchet format and allow you to visualize it on the terminal. Here's the functionality we provide nowadays in Proton. The example is showing profiling your kernel's running time. It's a call path profiling functionality, meaning that we're mainly going to profile your kernel's running time and aggregate it upward on every context. We support both Python context and shadow context. In Python context, we're going to unwind your Python call stack at every kernel launch, and then after profiling is done, we're going to aggregate metrics at every frame at your call path. Instead of using Python context, which supplies you long name, which consists of the path of the file name, as well as function name and line number. Sometimes we want to give some more brief name, like name it with the phases or some semantics of your Python script. For example, when you train a model, you probably want to group these kernels into phases, include forward, initialization, and backward. So I suppose some of you may have already been familiar with profilers, including Unsight System and Unsight Compute. Here's a brief comparison with Proton. So I compared them with regard to different perspectives, including overhead, profile size, profiling target, granularity, metrics, and Triton support. Let's start with the overhead comparison. So usually, Proton is going to introduce much less overhead than Unsight Compute. It's reasonable because Unsight Compute is going to collect numerous metrics. And it's also sometimes has lower overhead than Unsight System. As I have tested on some script with like millions of kernels launched in just few seconds, which are very small kernels, it still triggers only less than 1.5x overhead. The profile size, which is another unique feature of Proton, is going to be very tiny because it's going to streamline metrics collection at runtime. It's not going to dump you a very large database that consists of traces of every event. So the profile size, even if you launch it, even if your workload is going to execute for tens of minutes, it's still going to be just a few megabytes. Instead, Unsight System or Unsight Compute is probably going to give you a few gigabytes or even larger than that profile size. Although Unsight System can support GPUs and CPUs, Proton currently only supports GPUs, but it supports both NVIDIA and AMD GPUs. So when you use Triton to profile, use Proton to profile the same workload on different GPUs, you can easily compare their performance because we are going to apply the same profiling tool. Regarding the granularity, Unsight System profiles individual kernels, and Unsight Compute profiles kernels and instructions within kernels. Proton also has profiling functionality for both kernels and instructions. The next metric and the next thing to compare is metrics. Currently, we support profiling GPU time, GPU instruction samples, and some user-defined metrics. It is noteworthy that we don't profile every metric that Unsight Compute support. Instead, we just support a few commonly used metrics like instruction samples. We also have specialized support for Triton hooks. I hope this gives you a better understanding and comparison between Proton and other profiling tools. In the next, I'm going to dive into detailed usage of Proton's interface. So like I mentioned, it has two major interfaces, including instrumentation-based interface and command line interface. Using the command line interface, the usage is quite straightforward. We can either prepend Proton before your Python script and or invoke it as a Python module. But what makes it a bit more complicated is the instrumentation-based interface, which is our focus in this tutorial. At first, the first question we want to ask is, of course, how to start profiling. We can provide only interesting regions using Proton because sometimes your training workload or inference workload may be very complicated. There will be a lot of metrics or code regions you don't care about. We can just skip those regions in Proton. To start profiling, we call the Proton API, proton.start. The only profile name you want to profile if you don't want other functionalities, it's just a profile name, which returns your session ID. But if you only have one session, it doesn't matter. So once you know that the profiling is done, so you can output your profile using another API, proton.finalize. Like I mentioned, sometimes we want to skip some regions that not that interesting, but still accumulate the profile, the data to the same profile. Then here is why we want to use the session ID variable. We can deactivate the session profiling session by calling proton.deactivate. After that, all the GPU kernel costs will not be monitored. They are not going to be accumulated into a profile. Then after that, if there's some other regions we are still interested, we can reactivate it by supplying it as an argument to proton.activate. We use another tool called Proton-Viewer as a visualization tool. It's going to load the JSON profile data into Pandas compatible format and render it on terminal using Hatchet, which is a flexible package for performance data analysis. This has been maintained by Livermore National Lab. They have been supporting us. I want to just give special thanks to them. They have been supporting us for debugging and new features in Hatchet to support Proton. Hatchet can also convert the format into other formats, such as flame graph. Here's a simple view of flame graph it converted. For more usage of Proton Viewer, you can just use the -h option for more information. Okay, so in the next, I'm going to show you a series of examples to demonstrate how to use Proton to inspect the performance of your Triton programs. So to start profiling, we just talk about that we can use proton.start. It works even if you don't supply a profile name. Then the default profile name is just going to be proton.hatchet. The profile will be dumped into your current working space. In this case, we want to profile both initialization and the Triton kernel. Initialization will be done using PyTorch APIs torch.rand and torch.zeros. After that, we got three tensors, A, B, and C. Then we're going to invoke the Triton kernel add kernel we defined before to operate on these PyTorch tensors. After that, we're just going to finalize profiling by dumping the profile onto the disk. So the APIs here we involve are proton.start and proton.finalize. This is pretty much necessary APIs for every Python program you want to profile if you use the instrumentation-based method. After that, there's a simple view we can show on the terminal. The command we're going to use is proton-viewer-m, which supplies the metric name. In this case, the metric we are going to inspect is time, and it's followed with a slash, which specifies the unit we want to view about the time metrics, in this case, millisecond. And at the end, here's the profile name and its path. So on the terminal, here's what we can see. We can see there are three kernels invoked because we invoke torch.random twice. They are just going to be the same name, and their metrics will be aggregated together. And the kernel we care most is the Triton kernel, which is add kernel, and it shows that it spans 0.002 milliseconds. Sometimes we probably only care about performance of Triton kernels, but not these PyTorch kernels because they have already been optimized pretty well. In that case, we will invoke the deactivate and activate APIs that we talked before, which allow you to select interesting regions to profile. After starting profiling using proton.start, we get a session ID back. Then immediately, we are going to deactivate this profiling session so that we can skip profiling the PyTorch kernels. After that, right before the invocation of the Triton add kernel, we're going to reactivate the profiling again using proton.activate, with the argument being the session ID we just obtained. Then on the terminal, using the same proton-viewer command, what we can see is a clearer view, which only includes the add kernel. The next functionality in Proton I want to introduce is scope, which gives you ability to define user-defined regions with semantic information, which could be arbitrary names like initialization, forward, backward, whatever. And the usage is quite simple. It's just like a context manager. You can use it like with proton.scope, with the argument being the scope name. Okay, so here's the modification we need to supply by modifying our original script. Instead of monitoring the entire run, we are going to monitor each scopes individually, and also in the Proton view, finally we show we are gonna aggregate their metrics onto each scope. So we are gonna group these initialization kernels, including torch.randn and torch.zeros, into a phase or scope called initialization using this proton.scope utility. Then the add kernel is going to be grouped into another scope called add. After that, applying the same proton-viewer command, here's what we get. We can see that the add kernel is going to be grouped into the add region, and these randn and zeros kernels are grouped into the initialization region with their metrics accumulated on the left side. Using the scope utility, we can not only rename and group kernels that we are interested in, we can also supply metrics. So here are two kinds of metrics Proton can provide with. The first one is hardware metrics, which comes directly from the profiling substrates like CupT or rock tracer, for instance, kernel time or instruction samples. Proton also allows you to supply user-defined metrics, which are supplied by users. This includes things like expected number of flops, bytes, or number of tokens. So this is another field. So to supply the metrics, this is just another field in the scope API. Previously, we talked about that we can supply a name to rename the scope. But there's also another argument, which is a dictionary that you can supply to the scope API. This dictionary has the key with the metrics name and the value being the metric value. Currently, we just support metric value of integer or double. Then using this metric functionality, we can accumulate the number of bytes that have been accessed in each scope. In this case, we're going to calculate the number of bytes that can be accessed each time manually. So in initialization phase, we are going to access 3 tensors. So the total number of bytes will just be 128 by 128 multiplies 4 bytes per element multiplied 3 tensors. In the add scope, the total number of bytes we are going to access is 128 by 128 by 4 by 3, because we still access 3 tensors. Then we are going to run this function 10 times. In the end, what we can get will be a view like this, where it has 2 metrics, including the memory bandwidth in gigabytes per second, as well as the total number of access bytes. So each time we're going to access 196608 bytes, and since it's going to be run for 10 times, it automatically accumulates metric 10 times and provides you the correct total number of bytes. Okay, so here we have, until now, we have introduced the scope functionality and how do you start and end profiling sessions. After that, we are going to dive into a few more sophisticated examples to demonstrate Proton's capability. We're going to begin with renaming Triton kernels. So on the screen, here's a typical way we're going to write or define a matmul kernel with a few arguments, like a pointer to A, B, and C tensor. Its size, we suppose it's m by k multiplies k by n, and the stride of each tensor. Following it, we will have a few constant variables, including the block size, the group size, and whether or not we are going to use activation. So in Triton, if you still remember the workflow diagram, it's going to use the constant variable as a key to calculate the hash. That being said, although the function name you saw on the Python source code is matmul kernel, underlying it's going to specialize different kernel objects with different detailed names for each constant variables. In that case, actually the kernel objects will be different. For instance, if block size equals 16 versus block size equals to 32. So we are probably interested to inspect the performance of different specialized kernels. In addition, sometimes we are also interested in Triton kernel with different grid sizes, as well as the total number of warps used in each Triton kernel, which could render different performance with different number of warps. That being said, we want to rename a Triton function with a customized name, such as matmul underscore, with number of warps, block size, and the grid dimension. More than that, there are other things we want to do with each specialized Triton kernel. We probably want to associate each Triton kernel with metrics based on kernel arguments. We want to calculate the expected number of flops and the expected number of bytes invoked for each Triton kernel invocation. We can achieve this by using scope. However, it requires to instrument our script a lot if there are a lot of kernel launches. Instead, we offer a simple utility for you to achieve these functionalities, which is Triton hook. This is going to be an argument in triton.jit. It's a simple way to compute and associate metrics with each Triton kernel launch. What the user is supposed to supply is a metadata function. It's a callback function that takes 3 input arguments, including the grid, the metadata that includes warp, stages, shared memory, and other information, as well as the arguments that pass into this Triton kernel. It's going to return a dictionary containing renamed kernel name and other metric names and values. Here's a concrete example about how to define your metadata function. This example is already available online under Proton/tutorial matmul. So here we want to do 2 things. The first thing is to rename this Triton kernel to supply more information. We can just grab the values from the grid field to grab its grid dimension on X and X, Y, and Z. Besides, we can also directly obtain the number of warps and number of stages from the metadata variable. In addition to that, we can perform calculation within this metadata function to get the total number of expected flops, in this case 2 by m by n by k, as well as the total number of bytes, which is m by m multiplies n plus n multiplies k plus k multiplies m multiplies the element size. I want to point out that in addition to these calculations on CPU, you can even invoke a GPU kernel in metadata function if you want to calculate some specialized metadata quickly. Okay, so after applying this metadata function on top of the original kernel decorator, here's the Proton view we're going to get. We actually use scopes to annotate matmul shapes. In this case, what you're seeing is the kernel performance achieved by m equals 1024, n equals 1024, and k equals 1024. Using Triton's auto-tuner, we're going to run both auto-tuning phase and the final test case. We have already grouped them using Proton.scope, where you can see that their kernels fall into the auto-tuning scope, as well as the last kernel being the kernel achieved the best performance. For each kernel we see here, on the left side, we show its running time, and each kernel is renamed with metrics such as the grid dimension, the class dimension, the number of warps, shared memory usage, and number of stages, so that it gives you a better sense that which kernel actually achieved the best performance and what's the difference between this kernel and other kernels just have been tuned. The last coarse-grained functionality I want to introduce is roof-line-based utilization, which is something we can analyze using Proton. So unlike the normal flops utilization, which we're just going to compute the actual flops we achieved with the peak flops that we can achieve on this GPU, we are going to consider also the bandwidth limitation in the roofline model. So this is just give you a better sense about what roofline is if you haven't heard about it before. So I believe some of you may have heard it. So in the roofline model, we need to compute one important metric, which is arithmetic intensity. So we can compute arithmetic intensity for both the hardware and also the algorithm. To compute the arithmetic intensity for the hardware, like the GPU, we're going to use the maximum number of flops the GPU can achieve divided by the maximum DRAM bandwidth. Then the next thing is to calculate the arithmetic intensity of the algorithm, which is the expected flops versus the expected number of bytes. Then on the figure, we can see that if this arithmetic intensity of the algorithm is less than the arithmetic intensity of the GPU, then it falls into the memory bound case, which means that the peak flops cannot be the peak flops that can achieved by the GPU. Instead, it's limited by the memory bandwidth, so it's lower than the actual peak we can achieve. We can only use this for reference of the algorithm. Otherwise, if arithmetic intensity falls into the right side, which is greater than the arithmetic intensity of the GPU, then we see this kernel is compute bound. Next, if we want to calculate utilization based on roofline model, what we want to supply is the number of flops and number of bytes of this algorithm. Then the utilization matrix is calculated by flops per second versus maximum flops per second. Here, flops is just expected number of flops, which is calculated by user, divided by the time of this kernel. Then the maximum flops that can be achieved is the minimum of arithmetic intensity of the algorithm divided by arithmetic intensity of the GPU, and 1.0 multiplies the maximum flops. So after we are just going to use the same metadata function as we defined before. The only change here is that we are going to supply another metric, which is the utilization metric. We are going to visualize two metrics, including the utilization and the teraflops per second. So on terminal, what we can show are both the utilization as the first metric and the T-flops as the second metric. And as we shown before, you can see different utilization and T-flops achieved by different Triton kernels specialized with different arguments and kernel constants. Okay, so this ends up the coarse-grained profiler functionality. Next, I'm gonna give you another profiler functionality, which is a experimental feature. So this is the instruction sampling functionality in Proton. What we have covered before are just coarse-grained metrics, like looking at the flops of the entire kernel. or calculate the utilization of the entire kernel. If we have a large and very complex Triton kernels that could be thousands of lines, then we probably need finer-grained information about which lines, IRs, or instructions are expensive, instead of just knowing that this kernel is expensive. It's an experimental feature that we are developing to support this goal. Using NVIDIA's terminology, it's called PC sampling. So here's how instruction sampling works. It samples instruction on each active GPU SM for every n cycles. Each instruction is going to be associated with a store reason if available. It's going to tell you why the instruction is not issued, why it's taking a long time. Instruction sampling is going to trigger relatively low overhead with regard to each kernel's GPU time. That means if your kernel originally runs for something like 50 milliseconds, use instruction sampling, likely you'll still get 50 milliseconds or 51 milliseconds, which guarantees that what you profiled is true information instead of what has been dilated. It's already been available on NVIDIA, AMD, and Intel GPUs, but Proton only has integrated instruction sampling on NVIDIA GPUs by so far. Here's another diagram that helps you probably get more sense of how instruction sampling works. Suppose we have a Triton kernel that takes 7 out of 9 string multiprocessors on a GPU. Instruction sampling is going to work only on these 7 active string multiprocessors. It's going to sample instruction on every string multiprocessor for every n cycle. And when it's going to sample instruction, it takes sample from each warp scheduler in round-robin fashion. So suppose the first time it's going to take a sample, the sample is taken on scheduler 0. Then after n cycles, the next sample is going to be taken on scheduler 1, following with scheduler 2 and scheduler 3. Then it's going to take back scheduler 0 again. That's why it's going to take samples in round-robin fashion. And each sample it's collected could be in 2 states. It could be issued. That means the instruction is not stored anyway. But the instruction could be stored by many reasons. For example, it's waiting for a global memory load to be finished. It's waiting for other instructions to be scheduled. It's waiting for some very line mathematical pipeline or shared memory latency. Using these store reasons, you can probably look back your code and check what's going wrong there to optimize your code. Here's how Proton implements PC sampling or instruction sampling. It has 2 modes. The first mode is profiling in serialized fashion, which we're going to start instruction sampling before and after each kernel launch. It's a relatively simple method in which that we can accumulate metrics and attribute them to corresponding kernels correctly and simply. However, it's going to introduce relatively higher overhead. Another more fancy functionality we have developed but not enabled is continuous PC sampling. It allows you to start instruction sampling before and after each region without stopping the GPU kernel being launched and running. That means it's going to profile asynchronously until the point you call PC sampling stop. It achieves lower overhead and also allows even kernels running concurrently using 2 different streams on the GPU. But it does need auxiliary data structure or algorithm to attribute metrics because the same kernel can be invoked at 2 different contexts. Here's the overhead comparison when you use instruction sampling in Proton versus on-site compute. I use a simple tutorial offered by PyTorch, which is called Dynamic Net. This just defines a simple neural network with many small kernels. And using on-site compute, you can enable instruction sampling in 2 modes. The first one is to supply a option called --section source counter. Is going to collect metrics more than instruction sampling. So because it collects a lot of metrics, it's going to introduce very significant overhead. Originally, the PyTorch script runs for only 4 seconds, but after you enable this source counter section is going to be dilated to 66 minutes, meaning that the overhead is more than 1,000. You can also just sample metrics you're interested. For example, you are only interested in store reasons, like warp issue store weight. Then you can use -- metrics option to supply the exact metrics you want to supply. But in this case, you need to supply every metrics you are interested. Remember that we have talked about there are a lot of store reasons. If you are interested in all the store reasons, you need to copy paste all store reasons and put it on the command line. So I think it's a bit difficult to use. And more importantly, it still triggers high overhead. Using Inside Compute, it's going to introduce about 250x overhead. And I want to point out that most overhead is on the CPU and probably something in Inside Compute's tool instead of the API itself. Using Proton is relatively easy. The only command you want to supply is -- backend cupT PC sampling, which specifies that I want to start instruction sampling, following with the PyTorch script I want to monitor. So it's going to profile every store reasons by default. So it's easy to use, and it triggers relatively overhead using the serialized mode we introduced before, which synchronizes GPU kernels after it's being launched. It still triggers only 20x overhead. And I believe it can be reduced to less than 5x with the continuous mode. So using the example we talked before, which is a Matmo kernel, we want to look at its fine-grained metrics. Here, we use the same script and profile it using the PC sampling mode. But when visualize it, we need to supply a bit more advanced options, including -I, which is a filter option that includes in the final profile only call path passing through the match frames, and -T, which specifies the call path depth with a value greater than, this is not depth with, this is to specify the matrix that is greater only, that is call paths with a value greater than the given threshold. Here, the threshold is set to 1,000, meaning that only these frames containing more than 1,000 samples will be shown in the final profile. So after applying PC sampling profiling and visualizing on terminal, here's what we could get. We can see that for each Triton kernel, it has a few children. Those children are frames that down into each source line of the Triton kernel is defined with its path, its file name, its function, and its line number. So we have observed that the hotspots are on these lines from line 113 to 116. And by looking back to our Triton source code, we can see that these lines are loading data from global memory and also calculating value using TL. This matches our understanding and confirms that PC sampling can give us insights about where in our Triton kernel is spending long time. Okay, I think we can end up the tutorial a bit earlier. So to wrap up this tutorial bit, we have covered things about the interpreter and the profiler, including its basic usage, advanced usage, as well as some internal functionalities. All demos are, the code of all demos are available on GitHub. I think the slides will also be available, so probably you don't need to take a photo for now. There are two options to install Triton if you want to experiment with it locally. You can install it using pipwheel. It's convenient. However, not all features are available. Instead, you can also install Triton from source, try to build everything from scratch. But it may take a while. For example, it took about 10 minutes on my M3 MacBook. Besides, sometimes if you don't have good network connection, it could take even longer because we need to download a build of LVM. But to use all the samples, note that not all examples can be run directly in Jupyter Notebook. there are some examples, like the profiler example, may require that you build from source, as well as some privilege enabled to get performance counters. So you may encounter errors such as runtime error could not find libcupty.so, make sure it's in your LD library. This issue has been resolved in recent Triton updates. To resolve it, you just need to install Triton from source. There could also be permission problems I mentioned before. To resolve it, you can refer to this URL and following the instructions given by NVIDIA. I just covered what we have done by so far, but I haven't mentioned what's our roadmap or what's our plan. So the first thing we want to develop in near future is probably a performance analyzer. So currently, what Proton offers is just raw metrics. It can give you quick insights about what's expensive in Triton kernels or individual lines within Triton kernels, but it doesn't directly connect with what you could do as a kernel engineer or compiler engineer. Therefore, we want to collect more metrics, probably instrument directly into compiler analysis paths to emit performance warnings and associate these warnings with dynamic profile to provide guidance. There are already some warnings integrated into Triton, and we are looking for developing more warnings. The warnings is in the format like kernel.py with its line number and its warning message, factorization failed. Beyond that, we want to collect more fine-grained performance metrics because the GPU cores are becoming more and more complicated. So it's essential to understand thoroughly what's exactly going on for each warp or thread in a fine-grained manner instead of coarse-grained. So to achieve it, we want to collect time and other fine-grained metrics through LVM and MLIR instrumentation. All right, so in the end, I want to give some special acknowledgements to people who has been consistently support development of Proton and Interpreter, including OpenAI, who has been supporting the design and implementation of Proton and Interpreter, and AMD has been leading the development of RagTracer backend. Meta has provided qualitative feedback on tool usage and performance. NVIDIA has also offered advice and bug fixes for Cupty PC sampling API. All right, so the takeaways from this talk are that we can use Triton Interpreter to easily debug tensor variable values. Beyond that, we can use Proton as a profiler for fast feedback, lightweight profiling, and more insights about the calling context of each Triton kernel, the flops and utilization of each Triton kernel, and understand how Triton specializes each kernel source code. Yeah, that's it for the talk. Thanks.
Yeah, thanks, Keren. I'm so grateful that the Triton community is investing in tooling, and also the Triton conference is giving a spotlight to tooling because it's so essential for those toolings to help everyone in the community to move faster. So now let's move deeper into the stack. Let's welcome Haishan to talk about MLIR.
All right. Thank you for the introduction. Hi, everyone. My name is Haishan. I'm a software engineering manager at Meta. Very happy to be here, and it's really great to see so many people interested in Triton and working with Triton. So today, I'm giving a tutorial on creating a MLIR pass for Triton. So in this tutorial, I'll provide a taste of working with MLIR and its usage in the context of Triton compilation. This tutorial will not assume any compiler background or prior knowledge. It will assume you've looked at some Triton kernels before, but we'll walk through the kernels in quite a bit of detail. So not a lot of assumptions on prior knowledge. Here are the topics that we'll cover. We'll talk about MLIR background at a high level. We'll look at the Triton front end, some example Triton kernels, and the front end Triton IR that it generates. And then we'll dive into the main example of this tutorial, in which we'll create a MLIR pass for Triton. All right, so let's start with some background on MLIR. As many of you already know, MLIR stands for Multi-Level Intermediate Representation. It was originally a project started within Google by Chris Lettner, Maddie Amini, and many others. On the slide, I linked a paper that folks has published on this project. In this paper, they mentioned one of the main motivations for the project was that people has observed even within Google, within the domain of ML machine learning compilation, there were a lot of repeated work, and due to various resource constraints and so on, the wheels were often reinvented and sometimes re-implemented in a suboptimal way. And the goal of MLIR is to really create a reusable compiler infrastructure that is generally applicable to many, many use cases. And as a user of MLIR framework, I would say this goal is largely achieved today. If you take a look at the MLIR website and look at all the different use cases, you will see a large number of compiler projects that range from more traditional compilation to I would say more novel use cases such as high-level synthesis, language compilation for hardware design. So what is MLIR today, right? So if we dive into the code base, you'll see that it's really a very, very usable framework to build compilers. It comes with a large number of existing dialects, types, transformations, and analysis. And perhaps more importantly, it is very extensible with custom dialects, types, transformations, and analysis. It has its own PaaS infrastructure, diagnostic tools, testing tools, and so on. And one more important point I want to mention is it is also very easy to integrate the MLIR compilation flow into a LLVM backend compiler for low-level architecture-specific optimizations and code generation. So in case people have not seen what MLIR looks like, I just want to spend a couple minutes to just walk through what a very simple IR could look like, and later on we'll see more examples. So what on the screen is probably what a simplest IR could look like. It is doing a add operation. The arith part specifies the dialect. So this operation comes from a dialect called arith. The operation name is addf or add floating point. It takes two operands, %0 and %1. And the result that it produces is %2. On the right-hand side of the column, we specify the operands and result type. In this case, they are tensors of 1024 floating point 32s. There's only one field there because all operands and result happen to be of the same type. So taking a step back, what you'll see is, or what I want to mention is MLIR uses the notion of operations rather than instructions. So operation can basically mean anything from something that's complicated as a 3D convolution on tensors and filters and so on, or it could be as fundamental as integer arithmetic operations. Operations are opaque functions to MLIR. So what that really means is we can define operations to mean whatever we want them to mean, but at the same time, they'll have standard interfaces so that MLIR passes can work with operations that the authors of the past may have never seen before. You will notice that the IR is represented in SSA form. SSA stands for single static assignment. What that means is essentially each operation produces its own result, and we don't reuse names. So no other operation in this IR would produce another %2. This simplifies a lot of the compiler analysis. But what I would also mention is MLIR's SSA form might be a little bit different from what you see in textbooks SSA definition. Specifically, there's no notion of a fine node, but rather this is a lot of the complexities were handled differently using block args and control ops return values. And lastly, I want to mention that what's on the slide really is as simple as an IR could potentially go. But for folks who are more interested, I linked some slides that presented more comprehensive examples. You will see like operations could have various attributes. It can contain debugging information, and so on and so forth. All right. So I mentioned a lot of names, a lot of different concepts, but how do these things sort of compose together at the MLIR framework level? So one important concept to call out is the notion of dialects. A dialect is typically a collection of operations, types, attributes, related transformation passes, analysis, and etc., usually for a single purpose in a single namespace. I want to mention that multiple dialects can coexist within one module, and that's very much to the hybrid or multi-level nature of MLIR. In this last bullet, I'm listing some example dialects. Arith, math, the name are pretty self-explanatory. Func dialect defines operations that you will use to define functions, function calls, returns, and so on. LVM dialect defines a lot of the lower level operations that typically have a one-to-one mapping to LVM IR, and it's very, very useful when you integrate with backend compiler. Memref dialect defines operations for us to easily work with, memory allocation, deallocation, views, and so on. Types. So MLIR supports both built-in and custom dialect types, and I listed some examples below. And the last important concept that I want to mention is the notion of attributes. They are essentially in place constant data on operations. So some examples of attributes are comparison predicates, for doing a equal to, not equal to comparison. And in a Triton specific example would be if we're performing a boundary check on load or store addresses. I think this is the last slide on MLIR background. So how do these things put together, right? How do we use MLIR to actually represent a program? So MLIR uses a recursively nested IR structure. What that means is a single operation can contain multiple regions, and each region can contain multiple blocks, and each block can again contain multiple regions, and the recurses from there. So one example to demonstrate this is a Triton reduce op can potentially contain multiple operations in its body. And that allows us to express that we want to perform a relatively complicated reduce operations, even just with a single pass on the data. There are many different ways to navigate the IR structure, in addition to just iteratively visit each operation in program order. For one, MLIR provides mechanism to walk the recursive IR, and this is something that we'll see later in example. And MLIR also allows users to leverage the SSA nature so that we can easily traverse the dev use chains. The figure on the right, and apologies, I realized I lost the citation. I took directly from the MLIR website, and showcases some of these aspects that I just mentioned. So in this specific example, we have a block, which again, contains many operations. There's a begin and end pointer that marks the first and last operations in the block. A block can also have multiple block arguments. Within the block, we can again have multiple operations. Each operation can consume one or more operands or multiple operands, and it could produce multiple results. You'll notice that these operands are essentially just pointers to values. So, in the case of the middle operation, right, one of the values have 2 operands, and it's very easy for us to leverage the SSA nature to say, what are the uses of this value. And again, we'll see more examples down the line. Now let's switch gear to talk about more Triton-related background. So thanks to Keren, he covered a lot of great background, specifically, how the front-end compiler is structured. What I want to mention more is, after the initial front-end compilation, the Triton kernel will get translated into MLIR format using Triton dialect and some of the other standard dialects. And as we heard earlier, Triton defines a set of dialects, and the Triton dialect is one of them. Here on the screen, I'm showing some of the things that comes in Triton codebase that makes this dialect to work. In Triton types, we define a bunch of types that Triton operations can work with, from the things that are more familiar, like floating 32, integer 16, to some of the narrow precision data types. We also define integer types, tensor types, pointer types, so we can perform memory access on. In Triton ops, we define operations that often have one-to-one mapping from the language level constructs, like add pointer, where a key operation that we use to perform pointer arithmetics, loads, stores, dot to perform gem operations, and so on. And the list goes on. The Triton dialect also defines quite a few transformation passes to perform optimizations. It defines various interfaces and attributes for MLR passes to work on the corresponding types and operations as well. So let's look at, in the next couple slides, let's look at how a Triton kernel get translated into the front-end IR. We'll walk through this example line by line because this is an example that we'll use for the rest of the tutorial. So it might look quite familiar. It's actually a slightly simpler version than what Keren showed earlier. This kernel is trying to do a tensor scalar addition. So we define this add kernel. It has three arguments: x pointer or input pointer, y as a scalar value, and the output pointer. The block size is again a compile time constant. In the kernel body, we first take the program ID. We then use the program ID to calculate the offset starting from which this program is going to process the data. The offsets variable is a per element offset, so we calculate that by adding the block start with a range that starts from 0 and ends at block size -1. So to load the data, we add the base pointer, x pointer, with the per element offset. That creates a tensor of pointers, and from that we can load the data. To actually perform the arithmetic operation, we simply say x plus y, and what we're doing here again is we're adding a vector of block size with a scalar value that produces our output, and we're writing that back into memory. So this is what's on the screen is what the Triton front end would generate, and let's walk through this again. But at a very high level, you will see right away that the IR actually uses operations from multiple dialects. We see some operations from arith dialect to express constants. Add operations to perform either pointer arithmetics or numeric operations. But again, let's dive in. You'll see that the function is now from a TT dialect or Triton dialect func operation. We have the kernel name, and we shed the compile time constant, but we still have these three arguments. Now it's very clear the types of each argument. Arg0 or x pointer is a Triton pointer to floating 32, float 32s. Arg1 or y from the prior slide is again a scalar of float 32, and the output pointer is again just a pointer to f32s. Within the kernel body, we have the constant operation. So in this example, I arbitrarily chose a block size of 1024. So that's why we happen to have this constant here. But %0 is the program ID, which has a one-to-one mapping to what we saw earlier. We multiply using arith.mul_i to multiply the program ID with our block size, and that calculates our per program ID offset. tt.makeRange corresponds to the earlier TR range that creates a per element offset. And what's interesting here is, even in the prior example, right, we're directly adding the program ID, or rather the per PID offset with this range. But here in %3, we're actually splatting %1, which again is the per PID offset, and we actually add the result of this splat with the result of the make range to produce %4. You can see this pattern repeats itself in calculating the actual tensor of pointers. So we are splatting arc0 or X pointer to create another 1024 tensor of pointers, and we're using tt.addPointer to actually calculate the per element address. In calculating %7, we perform tt.load to actually perform the memory load. And then you can see the pointer happens yet again, right, where we splat arc1, which is our scalar value, into a tensor of 1024. And we use arith.addf to actually perform the arithmetic operation. All right. So now let's dive into the main example of this tutorial. So with all the background in mind, right? What we want to use as an example in the tutorial is we want to create a pass that replace tensor-tensor operation with tensor scalar operations when possible. So specifically, as you may remember from the last slide, we see these repeated operation sequences where we would splat a scalar to create a tensor, and then we would use the splat result to perform a element-wise operation. And the goal for this new pass that we're creating is to create this, to define and create this new instruction. Here I'm calling it myarith dialect .ts. This new operation will take a tensor as the first operand, a scalar as the second operand, and it will produce the tensor result. So why we might want to perform such a transformation? So many hardware actually natively support vector scalar operations, but at least at the arith dialect level, there's no built-in or native support for this. By performing such an optimization, we'll have fewer instructions to run, which is in general a good thing. We can also avoid potentially materializing %8 in this case, which are results of splatting scalars, and that can help potentially reduce on-chip memory pressure, reduce register pressure, and potentially help with the performance and the power. So in the rest of this tutorial, as I mentioned, we'll define a custom myarith dialect. We'll also define a custom add TS or add tensor scalar operation, and we'll define a simple pass to achieve this rewrite of a splat add operation sequence with our newly defined operation. So first things first, we like to start by defining the dialect. And just as a reminder, MLIR dialect is a group of related operations, types and attributes, transformation passes, and so on in a single namespace. We can define new dialects either using C++ by inheriting from MLIR dialect, or we could do it with TableGen, which is a handy tool for us to generate lots of codes. And that's the approach that we're taking. So we'll be creating a myarith dialect.td file. In that, we'll define myarith dialect, which inherits the MLIR built-in dialect. We'll give it a name, a C++ namespace, and a short description. And that's all it takes to create this dialect. Next, we'll define our new operation. So we're doing this again using TableGen. We will create a new file called myarith.ops.td. Inside of it, we're defining myarith.ops, which are essentially all the operations in myarith dialect. So we, again, inherit the base MLIR op, and we specify the dialect name, and we're basically just passing the mnemonic and the traits through. To actually define the new operation, we just need to define this myarith at tensor scalar op. We specify the mnemonics to be @_ts. We provide a summary, and in the arguments, we will explicitly specify the two input types, right, or the operand types. The tensor value is a ranked tensor of any floating point integers. Any floating points or integers. The scalar is just a scalar float or integer, and the result is of the same type as the tensor. Lastly, we provide a assembly format string so that the TableGen will generate a nice printer and parser for us, and our generated IR will be nice to look at. So we talked about TableGen a whole bunch, right? So what kind of C++ code does that actually generate? So here I grabbed a couple of screenshots for us to get a better idea. You can see we're defining this class called @scalarOp, and it inherits a bunch of traits in addition to, or rather, it inherits from the base MLIR op, and it already has a bunch of traits specified, all thanks to TableGen. We know from the definition that for example, it has no regions, it has one result, 0 successors, and so on. The TableGen also generates handy functions for us to work with the operation. We have nice getter functions, for example, getTensor and getScalar, that help us to grab the value that each @ts operation uses. And lastly, there's a handy function at the bottom of the screen that shows you how do we build a new @ts operation. To build this new operation, besides the boilerplate, we just need to specify the type of the result and the two values, the tensor and the scalar, and that's essentially all it takes. So coming back to finish, our example, the next thing we want to do is, of course, we actually want to define our path to do this rewrite. So here, we're using TableGen again. We create a new passes.td file. We define our convert Triton to myarith pass. We give it a brief summary, and in the dependent dialects section, we specify which dialect we will generate operations from in this pass. So in this case, it'll be our newly defined dialect. Now, to actually define this pass, we'll use the TableGen generated boilerplate code. And that greatly simplifies, the amount of code that we actually have to write as a human. But the main logic essentially is summarized, in the screenshot below. So the main function is this run-on operation, in which we will use the capability that MLIR provides for us to hierarchically walk the IR structure. So you can see we call get operation to grab the module op or the root op of the program, and then we can walk this recursively structured IR and call our rewrite splat at op only on Triton funcop, which, as you might remember, is the function operation that encapsulates our entire program. Inside this rewrite splat at op function, we're again, walking the IR structure. This time, we actually want to rewrite or we want to pattern match the splat op, and that's what this lambda defines. You will notice that in the for loop, we're iterating over the users of the result of splat. So that showcases, in MLIR, how easy it is to traverse the dev-use relationship. For each user, we check if it's a arith at f operation, and if we find a match, we know we found the pattern that we're looking for, and we can go ahead and rewrite this operation. To actually perform the rewrite, we essentially only have to call the build function that I showed earlier. So we instantiate our builder. We figure out which is the tensor operand. We already have the scalar operand as a parameter to this function. So that gives us all that it needs to create this @tensor scalar operation. The last thing that this function does is it replaces the use of the result of addf op, the original arith dialect op, with our newly created operation. And that essentially completes our rewrite. So putting this all together, what we have achieved so far, right? So we defined a new dialect called myarith. We defined a new operation, add ts. We created a new pass to manually pattern match the splat add sequence and rewrite them with our newly defined operation. To get this example to work, of course, there are some other changes that are required. We need to register the corresponding dialects and the passes, in this case, in Triton opt, which is the pass driver that the upstream Triton already builds. We could, of course, also do this on our custom pass driver. We need to make a few CMake changes so that we'll actually build our new files. And I include a link to a patch to enable this example in case you want to try it on your own. To see the custom passing action, you basically can walk through, in this specific setup, you can just walk through the normal Triton setup that Keren also mentioned earlier. And you can call the Triton or the MLIR pass driver Triton opt. You specify the name of the pass that we're trying to invoke, provide an input file, and it will supply the output file. Apologies, I didn't realize that we can't click the links, so I'll just describe what the output file looks like. What you will see in the output file is that there is a the new operation that we have created, insert right in the middle of the operation. It will take the scalar argument and the vector that we loaded from memory, perform the add tensor scalar operation, produce the result. What you'll also see in the output is that the result actually propagates to the tt.store, which is indeed what we intended, so that we can write the result back into memory. What you will also notice from the description so far, and also if you examine the first output, is that we never actually got rid of the operations that we're replacing, right? So we're replacing this splat add sequence. Those two operations are still in the first output file. So to complete this example, what we could do is we could either go back to our rewriting pass, making sure that these two operations have no other uses, manually delete them, or we could just call the canonicalization pass on top of our newly created pass, and that will remove all the values that have no uses and also no side effects. So in this tutorial, we walk through a very simple example on how to do a rewrite. There are many other considerations if we're to do this for real, right? Specifically, when we define the operation, we typically would want to specify verifiers. In this example, we might want to check if the tensor operand is a tensor of floating points. The scalar better also be a floating points. This so that we can fail at the earliest possible time to catch errors. We might want to define a better assembly format so the generated code is or the printout is more readable. We might want to specify the correct side effects. So in this case, we're not really writing memory, for example, and the correct interfaces so that canonicalization passes can also work with our newly defined operation. For the sake of this demo, we are using a very manual pattern matching and rewriting process. I want to mention that MLIR has a lot of existing established tools for us to achieve that goal. Specifically, we could use pattern rewriter. We could also use TableGen to create rule-based pattern matching and rewriting logic, and that will essentially eliminate any sort of manual codes. We're calling canonicalization, separately. There are arguments to be made in, calling that within the pass that we created, so that our top-level pass structure is clear. It is not always so. In this example, we're doing this rewriting at the Triton IR level, but depending on the compilation pipeline that you're working with, it typically takes quite a bit of thinking to figure out what's the best place to perform such a transformation. So, for example, you might want to do this after the operations have been vectorized to the architecture you're targeting. Lastly, we mentioned earlier, right, in the example, we saw this repeated splat add sequence. If we're to materialize the tensor of pointers, we could potentially extend this rewrite for pointer arithmetics as well. So with that, I have finished all the materials I have. I included a couple links for references in case people want to look into this topic further. Thanks a lot.
Thanks, Haishan. So that concludes the morning session. Lunch will be served at 11:45, and the afternoon session starts at 1. So enjoy.